This is a review of homework 7. Okay, here's the first question. Evolutionary theories emphasize that humans have adapted to their physical environment. One theory hypothesizes that people should spontaneously follow a 24-hour cycle of sleeping and waking, even if they are not exposed to the usual pattern of sunlight. To test this notion, 8 paid volunteers were placed individually in a room in which there was no light from the outside and no clocks. After a month in the room, each individual tended to develop a steady cycle. Their cycles at the end of the study were as follows. And then we've got some data from each of these 8 volunteers, so 25, 27, 25, 23, etc. Okay, so then using the 0.05 level of significance, in other words, alpha level at 0.05, what should we conclude about the theory that 24 hours is the natural cycle? And this is the critical question right here. That is, does the average cycle length under these conditions differ significantly from 24 hours? Okay, so in parentheses, this is really the critical question that we're trying to answer, is whether the average cycle length is statistically different than 24 hours. So then we're going to use the steps of hypothesis testing and sketch the distributions involved. So based on the information given, we know that we're going to do a t-test. Okay, and the reason is because we've got a population mean or a logical comparison value here of 24 hours. What we don't have is a number that gives us the variance in the population. So we're going to do a t-test. Okay, the two t-tests that we've learned so far are a one sample t-test, and then we've also we've learned a t-test for dependent means. And so we're going to use a one sample t-test because we're going to see whether this sample data, whether the sample mean that we're going to calculate from these data differs from 24. So we're going to do a one sample t-test. Oh, my animation is messed up. All right. So our research hypothesis will be that people who do not have natural sunlight will have a different sleep-wake cycle than normal folks that are exposed to sunlight. Okay, so our alternative hypothesis is that the population average, or mu, for people that aren't exposed to the regular sunlight is going to be different than 24. Where do we get that? It comes from this question. Does the average cycle length under these conditions differ significantly from 24 hours? There's no prediction about whether cycle length is longer. There's no prediction about whether cycle length is shorter. The question is the cycle length significantly different than 24? So we're going to do a two-tailed test, testing against this the population value under the null hypothesis, which is just regular people have a 24-hour sleep cycle. Okay, so the null hypothesis is that people who do not have natural sunlight will have the same sleep-wake cycle as normal folks that are exposed to sunlight. So that is, under the null hypothesis, there's no difference, there's no effect. People that don't get the natural sunlight, they'll be the same as everybody else that has this 24-hour cycle. So null hypothesis is that mu is equal to 24, and then under the alternative hypothesis or the research hypothesis, we're making the prediction that not having sunlight will result in a sleep-wake cycle that is somehow different than 24. Okay, so that's how we're setting up our null hypothesis and the alternative hypothesis. Step 2, we have to come up with our comparison distribution. Okay, so our comparison distribution is a distribution of means that is likely to occur if the null is true. So really what this involves is a thought experiment. We're going to imagine what would happen if we took every possible random sample of size 8 from a population that has a mean of 24 and a variance that we need to estimate. So in order to come up with the characteristics of our comparison distribution, okay, under the central limit theorem, we need to know the population average as well as the variance. Okay, but we've got some information, and so we can start to sketch out what our comparison distribution looks like. We know based on rule number 1 that we've been using so far that the mean of the distribution of means will be equal to the population means, so that comparison distribution will be centered around a mean of 24. We don't know what the standard deviation of that distribution of means will be because we don't have the population variance. So we're going to need to estimate that based on our sample data. And the other thing that we do know is that the shape of our comparison distribution will be a t-distribution based on 7 degrees of freedom. Recall that degrees of freedom are calculated as sample size minus 1. So sample size is 8 minus 1, we have 7 degrees of freedom. So we're going to have a t-distribution that is based on 7 degrees of freedom. The only thing that we need to figure out is what is the standard deviation of this distribution of means, otherwise known as the standard error. So we're going to get that standard error by coming up with an estimate of population variance. So we're going to take our raw data here. We're going to take each of these sleep-wake cycles from our 8 volunteers. We're going to calculate the mean, and we need that is because we're trying to say, like, on average, do people that are not exposed to sunlight have a different sleep-wake cycle than 24? So we're going to calculate the average from these 8 people. And so when we do that, we get a sample mean of 25. What we're then going to do is calculate the variance, and we're going to do that using our formula where we do a correction by taking the n-1 correction to get it, and we're going to use that to then get an estimate of population variance. So what we're doing here is the same procedure that we're used to doing, that I've shown in previous lectures and videos, where we're taking the deviations from the mean, we're squaring those deviations from the mean, we're summing the squared deviations from the mean. In other words, we're calculating sum of squares, the sum of the squared deviations from the mean. Previously, if we're just going to calculate variance as a descriptive statistic, we would just divide sum of squares by n. Here we're going to divide by n-1, in other words, degrees of freedom, and doing so allows us to then have a more accurate estimate of population variance. And then if we want, we can also take the square root of 1.43. That would give us an estimate of the standard deviation in the population. Okay, but for our purposes, this estimate of population variance is what we're interested in. All right, so moving on. Here's what we've got so far. We've got a sample mean of 25. We've got a comparison population. So our comparison population has a mean of 24, and what we've just come up with is an estimate of what the variance in that population should look like. So then based on these numbers, we can come up with our numbers for our comparison distribution. That is, what will our distribution of means look like? That distribution of means will be centered around a mean of 24, and now we're going to calculate the variance of the distribution of means as well as the standard deviation of the distribution of means. Rule 2a will allow us to calculate the variance of the distribution of means. All we do is divide the population variance, 1.43, by our sample size, which is 8. Again, very important that we're just using sample size here. We're not using degrees of freedom. So we've got 1.43 divided by 8 gives us a variance of our distribution of means that is 0.18. And then to get the standard deviation, all we're going to do is take the square root of that variance. In doing so, we get a standard deviation of the distribution of means, otherwise known as standard error, of 0.42. That's going to tell us, on average, how much can we expect any sample mean that we randomly sample to differ from the mean of the distribution of means. Okay, so it's the same interpretation as a standard deviation. It's just a standard error. Okay, a standard error in this case is 0.42. That would not be an unusual amount for any mean that we could sample to differ from 24. All right, so there we've got our characteristics of our comparison distribution. Okay, and we can sketch that out, right? So we sketch out this t-distribution that is centered around a mean of 24. And what I put in here is that we've got a t-value of 0, because we know, much like a z-score, if you're right at the mean of the distribution, you will have a t-value that is 0. Okay, so now we're going to determine what are the critical values on this t-distribution that separate the top 2.5% from the bottom 2.5%. How do we pick these values? Well, because we set our alpha at 0.05, and because we're going to do a two-tail test, that means we're going to split that alpha of 0.05 into 2.5 and 2.5%. Okay, so we're interested in the top tail of the distribution as well as the bottom tail of the distribution, because with our hypothesis, we specified a non-directional hypothesis. We're kind of saying we just expect that the mean among people that don't get sunlight is going to be different than 24. Could be a longer sleep-wake cycle. It could be a shorter sleep-wake cycle. We don't have a prediction. We're just going to guess that it's different. And so what we're going to do is we're still going to follow the rules of statistical significance testing, which is that by convention, a statistically significant result is one that happens less than 5% of the time, assuming that the null is true. Okay, so we're still going to keep that alpha level of 0.05, and so to have a two-tailed test, we just split that 0.05 into 0.025 and put that 0.025 in both tails of the distribution. So the question becomes, what t-value is associated with the top and bottom 2.5% of the distribution, of this comparison distribution? To determine that, we need to look at our table of critical values. So these are critical values, otherwise known as cutoff scores for the t-distribution. We're doing a two-tailed test, alpha 0.05. That means we've got that 0.05. It's split up into two tails. We're going to use degrees of freedom 7. And so just looking at the value in the chart, we're going to have plus and minus 2.365 as our critical values. And there they are. So we're just inserting them in our sketch. All right. So what we're going to do when we calculate our t-statistic is to establish statistical significance, we're going to be looking for a t-value that is either more positive than positive 2.365 or more negative than negative 2.365. In other words, we need a t in order to have a statistically significant result. We need a t that falls in this critical region or that falls in this critical region. So let's see what we get. To determine our sample's t-score, we start with our mean, and then we take basically our test value here, what we're comparing it against, which is 24, and then the bottom or the denominator of our t-statistic uses our standard error. Okay, so here's our t formula. It's the difference between our sample mean and the population mean under the null hypothesis divided by the standard error. That is, how much of a difference is reasonable to expect just by chance or by sampling error alone. So we're going to evaluate the size of this difference based on kind of like the amount of error that you could reasonably expect just due to sampling error. Okay, so plugging in our numbers, we get 25 minus 24 divided by 0.42. So that results in a t that is positive 2.38. Okay, so now last step, we're going to decide whether to reject or fail to reject the null hypothesis. We do this by comparing the t-score, the actual t that we calculated in step 4, to the critical value that we came up with at step 3. What we can see is that the t that we calculated does in fact fall in this critical region because it exceeds our critical value. So we are going to reject the null hypothesis, and we will always, 100% of the time, reject the null hypothesis if our test statistic exceeds a critical value in the expected direction. And that's what we have here. So what can we conclude in everyday language that somebody that doesn't know statistics could understand? what we can conclude is that people that are not exposed to natural sunlight develop a sleep-wake cycle that is longer than people exposed to normal sunlight. And we're making this conclusion based on what would happen in a population. Okay, so we're saying not just our sample of 8 people, but we're saying among like all people at a population level, the evidence that we have in our sample would lead us to believe that at a population level, people that are not exposed to sunlight will develop a sleep-wake cycle that is longer. Okay, why do we say longer? Well, because the mean was 25. It's greater than 24. That's a longer cycle. Okay, so we can interpret the direction of the effect once we've done the study. Okay, so that was our first problem. Here's our second problem. 5 sophomores were given an English achievement test before and after receiving instruction in basic grammar. So here we can see 5 students, and then we've got their English achievement test scores before and then after receiving instruction. Is it reasonable to conclude that future students would show higher scores after instruction? And I mean, this point is just to come back to something that I've tried to emphasize, is that we're not just interested in these 5 people. We're trying to make an inference. We're trying to make a generalization about what happens at a population level. So we're trying to say, like, hey, for future purposes, does this instruction seem to have an effect, not just among these 5 people, but in general? Okay, so we're going to test this question using the 5 steps of hypothesis testing. We'll sketch the distributions involved, and then, oh, I didn't have you do C, so skip C. We're not doing that. All right. So, a couple things. We've got our 2 different types of t-tests. We've got our one sample t-test, and then we've got a t-test for dependent means, also called a pair sample t-test. What we should be able to determine based on the structure of this problem is that we are going to do a dependent samples t-test. Why? Because we do a dependent samples t-test when we have 2 scores for each person. So we've got a before and an after in this case. So that is a research design that is appropriately analyzed with a dependent samples t-test. The next thing that we need to pick out here is the research question, which is that, is it reasonable to conclude that future students would show higher scores after instruction? So we've got a directional hypothesis here. The research hypothesis is that there will be some positive change after instruction. Basically, that scores should go up from before to after, okay? So that there's a positive change or a positive difference after this basic instruction. Animation's still messed up. Okay, so here's step 1 of hypothesis testing, is that we're going to state a null and a research hypothesis about populations. So our research hypothesis, and I often find it's easier to start with the research hypothesis because it's just translating that question into a statement. So the question was, is it reasonable to conclude that future students would show higher scores after instruction? Okay. So in creating hypotheses for a dependent samples t-test, it's about making a prediction about the average change. So our alternative hypothesis is that the average change after instruction will be positive, will be greater than 0. Okay? So to translate, students will have higher scores after instruction. That means from before to after, the numbers are going up. So there's a positive change. Okay? So the mean change after instruction will be positive. The null hypothesis is the direct opposite of that. Students will not have higher scores after instruction, which means that the change after instruction would be the same or less than 0. So like a negative change. In other words, lower scores or scores that are equal to 0 on average. Okay. Step 2, our comparison distribution is the distribution of means that is likely to occur if the null is true. Again, let's kind of close our eyes and try to do this thought experiment and imagine what would happen if we took every possible random sample of size 5 from a population with mu is equal to 0 and a variance that we don't know, but that we know we need to estimate. Okay? Why mu 0? Because under the null hypothesis, there's no change. There's no difference. So that's kind of our the value that we're always going to use as our comparison value when we're doing a dependent samples t-test. Okay, and so again, it's really doing this thought experiment and to ask ourselves, what would just happen if we randomly sampled 5 people and we did it again and we did it again and we did it again? What would be kind of the amount of change that we could expect just from 5 random people, even if the null is true? That's what our comparison distribution is going to tell us. So that comparison distribution is going to be centered around a mean of 0. The shape is going to be a t-distribution with 4 degrees of freedom. That degrees of freedom, again, just comes from sample size 5 minus 1. 5 minus 1 is 4. And then similar to the last problem, we just need to calculate the standard deviation of this comparison distribution, otherwise known as the standard error. And we're going to do that by using our sample data to estimate the population variance. And then once we have an estimate of population variance, we can use that to estimate the standard error. Okay, so we go to our raw data. We've got our before and after. So what we're going to do first to do a dependent samples t-test is we're going to calculate change scores. And then our change scores become our data. So in many ways, the dependent samples t-test operates just like a one sample t-test once you've got your change scores. Once you've got your change scores, you calculate the t-statistic in pretty much the exact same way. Okay. So we're going to calculate change as taking after minus before. So we're taking 18 minus 20 to get a change of -2. So this reflects that from before grammar instruction to after, this student's test score actually went down by 2 points. Okay, same thing. We're going to do after minus before. We're going to do 22 minus 18 to get a value of +4. Okay, so what happened is that from before to after, so after instruction, test scores improved by 4 points. There was a positive change. So it's important that you do that subtraction in a consistent way for all of your scores and that the numbers are reflecting what happened from before to after. So this is something that's really important just in doing all of these subtractions, that you eyeball each one and make sure that the value that you have for the change score kind of matches what you see. It's like, did student D, what happened to their scores? Did they improved by 1 point, so they've got a change of +1. What happened to student E? Well, their test score went down by 3 points, so they've got a change of -3. Can't tell you how many students I have do this incorrectly on the exam because they either don't subtract in the correct way or they subtract in an inconsistent way. So especially when the numbers are small here, again, just take your time and eyeball. Okay, do we have a change of -2? Yes, we do, because the test score went down by 2 points. All right. Once we've got our change scores, we're going to calculate a mean. Same thing, is very important to properly capture the negative and the positive numbers here. So when we sum those up and then divide by 5, we're getting a mean that is on average -0.4. So this should already tell us a little something about whether our hypothesis is going to be supported or not. Recall that we predicted that there would be a positive change after instruction. Well, we can see right now there's not a positive change. So in many ways, we've already failed to find support for our hypothesis, but we're just going to carry out all the steps here and calculate our t. All right, so next thing we're going to do is we want to be able to calculate a variance. And so same thing that we've done before, we're going to take our change score subtract the mean, get a deviation from the mean. Again, very important to do the subtraction in a consistent way. We're taking our change score minus the mean. So in this case, we're taking a -2 and we're subtracting a -0.4. So subtracting a negative is the same as adding a positive. So you can see that the deviation is -1.6 because we've essentially added a +4 by subtracting a negative. Okay, so again, make sure that you're doing those subtractions in a consistent way. Once you've figured out those deviations, square those deviations, take the sum of the square deviations to get sum of squares, divide by degrees of freedom in order to come up with an accurate, unbiased estimate of population variance. That's what our S squared is. So our estimate of population variance is 8.3, and then just for fun, I've taken the square root of 8.3 to get an estimate of what the population standard deviation would be, although we're not going to use that number for our future calculations. So we could, if you want, you can just have stopped right there at your estimate of population variance. So here's what we have so far. We've got an average change in our sample of -0.4. So on average, test scores actually went down by 0.4 points. Our comparison population under the null hypothesis would have a change of 0. We just figured out that the estimated variance in this population would be 8.3. Our comparison distribution, that is the distribution of means that would be formed by taking every possible random sample of size 5, will be centered around a mean of 0. And now we're going to use our estimate of population variance to figure out the variance and the standard deviation of this distribution of means. So using Rule 2a and Rule 2b, same calculations as before, we get that our estimate of standard error is 1.29, and it's this estimate of standard error that we're going to use as the denominator of our t formula. So there we've got it. We've just filled in our estimate of standard error. So these are all the characteristics of our comparison distribution. All right, to determine our critical value, we're going to sketch our distribution. Here's our distribution of means centered around a change of 0, which is equivalent to a t of 0. We're doing a directional test in which we predicted a positive change, that is an improvement of test scores. So we're interested in this top 5% of the distribution, 5% because we specify that alpha is 0.05, degrees of freedom 4. So we're going to use our t-table, our table of cutoff scores, to come up with the t-value that we need as our critical value that is associated with the top 5% of the distribution when degrees of freedom is 4. All right, so looking at our one-tailed test, alpha 0.05, degrees of freedom 4, we get a critical t of, in this case, it will be positive 2.132. Okay, so there we are. There's our critical value. This is the value that we need to exceed. With a mean that is negative, we should kind of know in our brain already that we're not going to get a positive t, but we'll still carry out the calculations. So our comparison number is 0, and our standard error is 1.24. All right, so our t is calculated as our sample mean minus the population mean under the null hypothesis divided by standard error. So we get -0.4 minus 0, called it under the null hypothesis for a dependent samples t-test. The default value here is always 0 because we're saying 0 change, dividing that by 1.29. So that gives us a t statistic that is -0.31. And just locating that in our distribution of means, we can very clearly see that when our mean is converted to a t, that very clearly does not fall in the critical region. So we are not exceeding our critical value, and so we're going to fail to reject the null hypothesis. Okay, and so in language that somebody that is not familiar with statistics could understand, there is inconclusive evidence to suggest that students get higher achievement test scores after grammar instruction. So based on this study that we did with 5 people, we would have to say that there's inconclusive evidence that the instruction works. We want to stop short of saying like, well, it's definitely true that the instruction doesn't work. I mean, the instruction could work, and if we had a larger sample, maybe that's what we would find. But right now, we would just say, based on the small study that we did of 5 people, there's inconclusive evidence from these 5 people from our sample data to reject the null, and therefore we fail to reject the null hypothesis. For the time being, we have to accept that the instruction doesn't work based on these data. All right, and the last question is to figure out effect size. And so we've got a table of data, and what we're going to do is for each of the A, B, C, and D, we've got predicted mean change. So we can think here of doing a dependent samples t-test because we're talking about mean change, and then we're given a population standard deviation. So we've got several formulas for effect size, and they're all pretty much the same, is that we're looking at a difference between a sample mean and then a mean value under the null hypothesis divided by a population standard deviation. So in this case, because we're dealing with mean change, we're going to use our effect size formula that is appropriate for a dependent means t-test. So what we're given in the table is the mean predicted change. We're going to subtract mu2, which is always 0 when doing a dependent samples t-test. We don't actually have to use an estimate of population standard deviation because we've been given that. Okay, so we're essentially using this formula. And then our conventions for calculating this D is that 0.2 is small, 0.5 is medium, and 0.8 is large. All right, so here's our calculation. So with a mean predicted change of 8 and a population standard deviation of 30, we'll just do 8 minus 0 divided by 30, which gives us a D of 0.27, which we can say is small, or I'll just say small-ish, because our convention for smallest is 0.2. So, there is some amount of subjective judgment that's involved in putting a label of small or medium at times. So we'll say this is small or smallish. Second one, we're going to take that same predicted mean change, and now we only have a standard deviation, which is 10. So you can see actually that same difference is a larger effect because we've got less variability. Okay, so that there's actually less overlap between those two population distributions because the standard deviation is less. So that yields a D, which is 0.8. That's a large effect. Next one, we're basically just using the same basic formula. You should get a D of 0.53, which is medium. And then for D, you get the last effect size you get is 1.63, which is large. All right, and that's the last one. So hopefully you found this video helpful in reviewing your homework. I will see you for the next one.